In this video, I want to start talking about rational functions. So a rational function has the form r of x equals p of x divided by q of x. So p of x and q of x are polynomial functions and q of x cannot equal 0. Okay, because if q of x was 0, we're looking at a fraction right here. If the denominator was 0, the entire thing is undefined, so we have to make sure that q of x is not 0. Okay, and that's really our domain. So the domain of a rational function is all real numbers except, I'm going to capitalize that, except, I'm going to double underline it, where q of x equals 0. Okay, so we can plug in any real number we want to, except whatever is going to make our denominator 0. Okay, so let's look at a quick example of finding the domain of a rational function. Let's say we have r of x equals x squared minus 4 all over x plus 4. So if we're just asked to find the domain, my concern here is that x plus 4 does not equal 0. So I can take my denominator, x plus 4, and say it's not going to be equal to 0, and then just solve it like a regular equation. So here, x cannot equal negative 4. And then, to write our domain formally, we can say x such that x does not equal negative 4. Okay. As another example, we could have r of x equals to x plus 6 all over x squared plus 8x plus 12. So looking for my domain here, I have something that's quadratic in the denominator. So really, the first thing I want to do is factor that. So I'm looking at the factors of 12 that are going to add up to 8. So that's 6 and 2. So here I've got x plus 6 times x plus 2. Okay, now that my denominator is fully factored, I can look for my domain, and that's whatever makes these 0. So I can say x plus 6 cannot equal 0, and x plus 2 cannot equal 0. So here x cannot equal negative 6, and here x cannot equal negative 2. If we wanted formal notation, we could say x such that x does not equal negative 6, and x cannot equal negative 2. So it's important that we find the domains of our functions. We really want to find the domain of a function before we reduce it. So here I factored. This reduces right here, the numerator and denominator. But when I'm looking for just the domain, I don't want to reduce anything first. I want to leave it, I want to leave all of my terms in there so I can see what my domain restrictions are. Okay? We'll talk about these two crossing out in the next video. But before we move on, let's look at a parent graph. Let's look at the graph of f of x, excuse me, equals 1 over x. Okay. Well, before we graph or plot points or anything like that, we can say that there are no x-intercepts. Since f of x cannot equal 0, okay, and there are no y-intercepts, since f of 0 is undefined. Okay, so I can't set this equal to 0 and solve for x. That's not going to result in any kind of solution. And I also can't take 0 and plug it in for x because that's going to give me something that's undefined. Okay, so let's make a t-chart real quick. And I'm going to pick numbers that are really far away from 0 and then really close to 0. I say really far away, but for our purposes, they will be. Let's say -1 and -1 over 100. Okay. Then let's use 0, and then we'll use 1 over 100 again, and then 1. Okay, so here at 0, we know that this is undefined. It doesn't exist on our graph. Now, if I take -1 and I plug it back into my function, I've got 1 over -1, and that is just -1. If I take -1 over 100 and plug it in, I have 1 over -1 over 100. And remember, when I have a fraction inside of a fraction, I take the reciprocal of the denominator and multiply it back to the numerator. So that equals -100. The same thing if I take +1 over 100 and I plug it into my function here, I end up with +100. And then if I take +1, plug it back into my function, 1 over 1 is just 1. Okay. So why did we do that? What did this tell us? The closer I get to 0 from the left or the right, the higher up or further down my graph is going to be. Okay. So let's say that I had 1 right here. I'd be super far up here at 100. I'd be coming down. Then around 1, I'd have a value there at 1. And then I would keep going. And since I can't make this equal 0, the further away I get from 0, so if I were to take +100 and plug it in here, it'd be a very, very small number like I had here. Okay, so it's just going to get smaller and smaller and smaller as I move this way. It's going to get taller and taller and taller as I move up the y-axis. Okay, and the same thing with my negative numbers. The closer I get to 0, the further down I'm going. So I'm way down here. I'm going to get closer and closer. I'm going to cross through the point 1, 1. And then the further away I get from 0, the smaller my number is going to be. So if I take -100, here I've got 1 over -100. So I'm getting smaller and smaller and smaller. Okay. So this is what my graph is doing. Let me highlight some things. Here, for this function, I'm never going to actually cross the y-axis. So I'm going to kind of put a dotted line right next to the y-axis. So I'm never actually going to cross over the y-axis. I'm just going to keep getting taller on this way and smaller going this way. Same thing over here. I'm going to keep getting further down the closer I get to 0, and then the further away I get from 0 on the x-axis, the smaller my number is going to get. So I'm also not ever going to cross the x-axis. So I'm going to use a dotted line right here just to show us. Okay, so remember, our special lines are just x equals a number and y equals a number. So here, where x equals 0, I have this vertical line right here that I cannot cross. And where I have y equals 0, I've got this horizontal line I cannot cross. These are called asymptotes. Okay. So my x equals 0 here is a vertical asymptote. And my y equals 0 here is a horizontal asymptote. Okay, so you can kind of think of them as lines that our graph does not cross depending on what they are and where we're looking. So thinking of that graph f of x equals 1 over x as a parent function, let's look at f of x equals 1 over x minus 3. So we had our t-chart for 1 over x. I'm not going to reuse all of those numbers. I'm just going to use -1, 0, and +1. Here we found our answers to be -1, undefined, and +1. So this was slide work. Now, thinking about all of our transformations and shifts and such, we still have those same ideas. Right here, I've got 3 being subtracted from x. So I can think of this as shifting my graph 3 to the right. So I can do +3, +3, +3. Okay? Nothing's being multiplied, nothing's being added, so I'm not moving up or down or stretching or shrinking. I'm just shifting left and right here. So my new t-chart for 1 over x minus 3. So -1 plus 3 gives me 2. 0 plus 3 gives me 3. 1 plus 3 gives me 4. And here on my y's, I'm still at -1. Here at 3, I'm still undefined. And here at 4, I'm still at 1. So to graph this, I still have my horizontal asymptote y equals 0. I'm still not going to cross over that. But now, where I'm undefined is y equals 3. So 1, 2, 3. X equals 3. I'm sorry. So now my vertical asymptote also shifted 3 places to the right. Okay. So now I can just fill in the rest of my graph from what I know. So our shifts left and right, our transformation stuff still works. It's a little bit different for some things, but we will keep talking about that. I would like to continue talking about the asymptotes. For now, okay, just be aware that our asymptotes will move along with our shifts, but we still have to find them. The other way we could have found this asymptote was just to set this denominator equal to 0 and solve for it. That would have given us x equals 3, and that's where my asymptote is. Okay, so let's talk about types of asymptotes for a minute. So we have vertical. A vertical asymptote describes the behavior of the graph close to some number c. Okay. So by some number c, if you think about what we just graphed here, c would be 3, and my vertical asymptote is telling me what's happening near 3. Okay, so to the left and right of it, I'm going up to infinity and down to negative infinity. Okay, also, the graph will never intersect a vertical asymptote. Okay, never, never, never. Then we have a horizontal asymptote. So a horizontal asymptote describes the end behavior of the graph. So as x approaches infinity or as x approaches negative infinity. Okay, so looking here, my horizontal asymptote is y equals 0. And as x approaches infinity, which means as I keep going right, I'm getting closer and closer to 0. And as I'm moving left, closer and closer to negative infinity, I'm also getting closer and closer to 0. So my horizontal asymptote here is y equals 0, because it's talking about the end behavior. And since it's only talking about the end behavior, it is possible that a graph will cross a horizontal asymptote. Because remember, it's only talking about the endpoint behaviors. We have one more, and that is called an oblique. Sometimes some people will call it slant asymptote. Okay, and for my oblique or slant asymptote, as x approaches infinity or as x approaches negative infinity, the graph of f of x approaches a linear equation. So something ax plus b. I'll write a linear expression right there. It is possible to cross an oblique. Because again, we're talking about as x gets really big or really small, so we're talking about the infinities, we're only talking about the end behavior. And just as a small example, if I have room here, this was my graph. I could have an asymptote such as this, the line y equals x, and my graph could be doing something like this. Okay, so the further and further I go towards infinity, it's just going to stay along this line. It's going to get closer and closer to this line, but never actually there as I'm approaching infinity. So you may see it crossing sometimes. Okay, so in the next video, I'll talk about how we find these different types of asymptotes.